Hi, everyone. My name is Erik Osheim, and welcome to my talk. So my talk is called Functions of Determinism in Property-Based Testing. And I guess before I really get into it, I'm just curious, how many people do property-based testing, either on their own projects or at work or something? Okay, so maybe a third of people. How many people have heard about property-based testing and think it's cool even if they don't use it, for example? So basically, okay, about a third. So basically, everyone who's heard about this thinks it's cool and uses it, which is a great success rate, but maybe a bad kind of evangelism story as far as coverage. So who am I? Well, so I'm a member of an organization called Type Level. It's not like a company or anything like that, but it's about supporting pure functional programming in the Scala open source community. I maintain Spire, CATS, and a number of other Scala libraries. Exciting note, as of Monday, I am a ScalaCheck co-maintainer. So I'm super jazzed about that. I have this is something I always say, and maybe it gets less true over time, but I have kind of a dual interest in expressiveness and performance. Sometimes people go in one direction or the other, but I think it's important to try and do both as much as possible. And for my day job, I support efforts at machine learning and fraud detection at Stripe. So that's what I do outside of open source. And you can see some of my projects at my GitHub page here. And so what will this talk cover? So there's 6 points here. There's going to be kind of a pretty brief overview of property-based testing and some case studies of it. And then the thing I'm really interested in this talk is generators. So how they work. I would like for people to come out of this talk with a good idea of how generators work and feeling confident that they understand what's going on. That's my main goal. The function generation is this really cool thing that really blew my mind, and I'm hoping it will blow yours or at least get you a little bit excited. I then kind of want to finish up with some takeaways from the talk, and hopefully you'll be enthusiastic about testing, and specifically this kind of testing. Now, one proviso here is that this probably should be 2 talks. You could do a whole talk just about what property-based testing is and how you do it, kind of a sort of tutorial level talk. And initially I thought I could do that, but it turns out in an hour I don't really have time to do that and really dive into generators. So I'm going to kind of give short shrift to the how you would do this. There's a lot of good tutorials out there, and hopefully, if this excites you, you can explore them. But if it doesn't, I sort of apologize for that. So what's the overview? Well, ScalaCheck, Quick Check is the real origin of property-based testing, and the paper around it was published in 2000. I think Quick Check had already been in use for a couple years by this point, but this is sort of the paper at ICFP that really, I feel in retrospect, kind of caught the world by fire. This was one library in Haskell, which at the time wasn't a very popular language, and now it's huge. It introduces most of the things we still use. So we talk about properties and generators. People talk about shrinking. All these things are mentioned in that paper. So that's a pretty great paper. I recommend it. It's also very readable. It's not very long. And at this point, after that paper, here's the situation. Whatever language you work in, there's definitely at least one library that does this. They sometimes vary in quality. Here's just a sort of sample of what seemed the best in each language. But it exists. So if you want to be doing this, but you write Ruby, there's totally a way you can do this in Ruby. And actually, the talk is in Scala, so I'm assuming some amount of familiarity to read anonymous functions and stuff, but it doesn't really use much advanced Scala stuff, and it's really not Scala specific. So if you can understand the idea in the talk, you could go and do it in JavaScript or in Perl or whatever language you work in. It's really, hopefully, very transferable. I did not use a lot of JVM specific stuff, whenever possible. So when we say property testing, what do we mean? Well, the basic unit is a property, and I think a pretty productive way to think about it is basically a property is a function that returns a Boolean, and we want to say that for all values you could pass it, it will always return true. We don't know if that's true, but we would like for that to be true. And basically the idea is that if it really does return true for all the possible values you could pass it of a certain sort of shape or whatever, then the property is true and our idea about the universe is correct. But if we find any case where that's not true, then we're wrong and the test fails. And the real unfortunate secret is that usually we cannot exhaustively test these things. So for large spaces, you can never exhaustively check every single value. So what we're really doing when we do property testing is we're searching for failing cases. We're searching for counterexamples that prove that we're wrong about the universe. It's a little bit like physicists, right? They're going out there looking for data because they want to be wrong, which requires a more interesting theory. And just to kind of restate this in a different way of thinking about it, properties are possibly true or definitely false. In other words, once we find a failing case, we know it's false. It's hard to be sure that it's definitely true. We might think it's true, but we could be wrong. And this is kind of related to this idea that Dijkstra brings up, where he says, program testing proves the presence of bugs, but can't prove their absence. This is sort of a more specific point about that general truism. So when we test a property, what do? Well, really, we choose how many sort of passing cases we'd like to see to kind of feel okay about things. We generate that many test cases. We evaluate our property for each of those test cases, and if they all pass, then we're fine. But if a single one fails, then the property is falsified. And at that point, we have some intellectual work to do. Like we have to determine like why it failed, and what that does to our theory of the universe. One interesting note I put is that we sort of want the test cases to be distinct. If we generate 100 cases that are all the same case, we haven't really proven that much. So just something to kind of keep in mind. And we base our confidence in our theory about the universe on the number of passing test cases. So like when you're doing this kind of testing, usually interactively, if we think we're mostly right and we just kind of want to be very agile, you might not run it that many times. You might say, if it passes 10 times or 100 times, probably that's okay. But then if we're about to publish a paper or something, you might really leave your machine running overnight and just crank through tons of cases to be really, really sure, or at least gain some amount of certainty because you have time and you want to do it. So it's an interesting trade-off with property-based testing that we sort of choose how many computational resources we'd like to put towards proving our theory. So that's like my real high-level overview. And now I just going to jump right into some case studies. These are all taken from actual projects, so it's actual code. So some of it's a little bit ugly, but hopefully it's readable. So the first case I want to show you is a library I wrote a while ago called archery. It's an immutable 2D archery implementation. So it gets used as like a spatial index for if you have a whole bunch of points and you want to be able to search that set of points very quickly, you could use this. There's sort of more advanced structures, but this one's pretty good. And I sort of linked the paper that describes the actual algorithm. And it's complicated enough that you would really want to test this, because if you just tried to write it, there'd probably be bugs. It's the sort of thing that it's hard to get right the very first try. So in this case, I wrote some properties, including this one, to try and convince myself that I had implemented the paper correctly. So in this case, what is our property doing? Well, our property says that we want to know if this nearest k method works. And how do we determine that? Well, we're going to generate a whole bunch of entries in our tree, entries like values that we're going to put in our tree, and we're going to generate some other point that we were going to search at, and then k, which is some integer. And what we're really trying to say is we want to find the k nearest elements in the tree to the point that we gave. And we want to be sure that we're doing this correctly. And so what do? Well, in the test, we sort of build an R tree, but then we also just search the entries directly. So the expected is sort of this is simple but not optimized. We're just using a list. We're going through the list, finding the distance from p to every single entry, sorting that to get the sort of shortest distances first, and then taking the top k of those. And saying, OK, if we did things the slow way exhaustively, this is what we would get. And then we use our R tree, which in theory should do the same thing but much faster. So we're finding the nearest k, and then we're mapping those things we got back to the distance from p. And we want those two vectors to be the same. If those are the same, then that means it's some evidence that nearest k works. If those vectors aren't the same, it means that there's a problem. And so at the end, we say that these two vectors should be the same. And so this is one I think. A lot of times when you see property-based testing, you get these examples that are make sure that addition is commutative. And we all know addition is commutative. We don't need a lot of evidence to believe that. And so I think it's an interesting example in that it's very succinct. But I think this is an example that's not that much more complicated, but it's a real world, real motivated example. And so what could this have caught, or what did this catch? And this definitely did catch bugs when I ran it. It was long enough ago that I can't remember the specific ones, but it definitely caught them. And if the R tree generation was broken, if it crashed building the R tree, that would have failed. Or if it built the wrong kind of tree, we would fail. If the searching wasn't correct, it would also produce different results. You could imagine situations where duplicate entries might be ignored, so you might only have one of them instead of two, if you used a set internally or something. And that's a situation where the list would give you different results than the search. And then finally, this is one that I think I do remember, is when I first wrote this, it couldn't handle searching for 0 points, which is sort of a dumb edge case. But on the other hand, it's nice to have the thing say, oh, I used k0 and your thing crashed or something, instead of returning an empty vector. And that's pretty interesting, right? It's kind of useful. So that's a situation where I just went back and changed the API real fast and it worked. Another case, we got this JSON parser that I wrote that's used by a bunch of other libraries. And I used property-based testing to try and ensure myself that it was correct. So here's a test that, how many people know what idempotence means? So maybe a quarter of people. So the idea of idempotence is sort of if you do something multiple times, it should be the same as if you only did it once. So if I validate something and then I go validate it again, it shouldn't change things. Right? Once I do this thing once, if I do it more times, it doesn't matter. And so idempotent parsing rendering here kind of means that once I parse something, render it, and parse it again, it's the same as if I parse it the first time. It doesn't change the data anyway. There's nothing interesting going on. That's what I mean by idempotence in this example. And so what we're doing is we start with some kind of JSON value, like in Java or Scala. We render it as JSON, like a string. We read it back in as a JSON value. We render it again as a string. And then we sort of make sure that all the things at each stage line up. So we didn't want to have it change. If it had changed, that would indicate that the library was either corrupting the data or somehow there was just like some weird formatting thing going on. Like I'm sure you've all experienced things where like you have a value that's like 123 that becomes 123.0 or something, and so like a diff fails, and you're just like annoyed because it's like, why did you do that? Like I didn't do anything to the data. Why shouldn't change? And so this test kind of ensures that that doesn't happen, as well as some other stuff. And so what could this have caught? This could have caught parsing bugs, rendering bugs. That sort of the exact case I mentioned, like 9 versus 9.0, could have caught broken equality, broken hash code. And could also have caught, if my string parser, my file parser had some weird problem where they weren't always the same, this would have caught that too. So I'm getting a lot of coverage with like one property, and that's sort of the thing that's hopefully you're impressed by, that you can test a lot of stuff with one property as opposed to writing a bunch of individual test cases. I have a couple more examples I'm going to breeze through a little more quickly. This one's about an interval type, so intervals, a range of values from like a potentially like lower bound to potentially upper bound, some values in between. And what are we doing here? Well, this test is a little interesting. Basically, I'm doing some operation on an interval, and then I want to be sure that all the points in the original interval, when I do that operation on that individual point, stay in the resulting interval that I got. So if I like if I square an interval, if I take an interval times itself, I get some new interval. I want to make sure that every point in the old interval, if I square that value, I get a point in the new interval. If I didn't, that would mean that the operation wasn't closed, that somehow some point was escaping, and that'd be a bug somewhere. And so test UNOP is like this framework thing, and I'm calling it twice with like squaring an interval and cubing an interval. And I want this to always pass. And if I find a situation where it didn't, that indicates that there's a bug in interval. And sample here is just sampling 100 unique values from this interval, the range of values. So that's another kind of property-based test. And this did also catch real bugs, in code that I thought was correct. And then the final one from Stripe at work is this n-gram iterator that we use for machine learning. So we're building text features. So we're looking for like bigrams or trigrams to get counts to build feature vectors. And so we have some code that does this. And this n-gram iterator is the thing we want to test here. So here's kind of an example of it running so you can sort of see it. And then the property, I sort of slightly modified it, but this is basically what we're doing at work. We build some random input data, like random text data. We build this iterator. We manually process the text in a kind of inefficient way using this like sort of range and flatMap and doing this sliding operation. But we believe this is correct, and then we have our fancy iterator down here, and we basically want to assert that we got what we expected, that doing it the slow way and doing it the fast way get the same results. It's a little bit like the archery example, where we have a slow but easier to see correct way and a faster, more tricky way, and we just want to make sure that they always do the same thing. So to sort of summarize it, and hopefully this is getting you excited about property-based testing, is there's a bunch of different kinds of tests we're doing. Like we're testing laws like idempotence or associativity. That's kind of the classical thing people talk about it. But we also have this parallel evaluation strategy where you might have some fast but easy to mess up code path and a slow but steady one. You can run both of those in your test and make sure they always agree. And that helps you have confidence that like your fasting sort algorithm or your fast search algorithm is the same as the naive one that's easy to see that it's correct. We also have some spot checking, like the interval example, where we're looking for specific places where it could go wrong, because it's hard to exhaustively test. And we're also just running the code. I mean, we're exercising the code for a wide variety of inputs, which if the code crashes, there's a bug somewhere. So that's another kind of test. And so really, I guess the takeaway is that it kind of forces us to think in an interesting way about how we would write tests. Instead of writing one test case, we think about how would I generate a whole class of tests? Like what's a pattern I could use to generate a whole bunch of tests to cover this space? Not necessarily exhaustively cover the space, but cover a lot of it, as opposed to like covering one little slice of it with one test and another little slice, another little slice, and you spend your whole day writing these little slices, and you still maybe don't have very good coverage there. And so what are we missing from this presentation so far? I've shown you these properties with this for all predicate, but the thing I haven't told you is how we even get these J values. Like, how did I even produce those in the first place? Like, it's nice once you have that, of course you can do some interesting tests, but how did you get them? And so the main thrust of this talk is that question. How do we generate values, generators? So all the motivation hopefully has already happened, because at this point we're deep diving into generators and there's no more motivation coming. So let's just, either you're convinced that property-based testing is cool and generators are interesting, or if you're not, like, please humor me and act like you are, right? Because from here on out we're just doing it. So yeah, so generators. And just to be clear up front, this is a simplified view of ScalaCheck generators. So I learned about this working on the actual ScalaCheck project, but for the presentation, I'm trying to kind of like simplify things to give us a clear picture of what's going on, as opposed to a lot of weird details. So we're not as worried about efficiency as we would be in real life. We're not worried about some like legacy API stuff that's just kind of crufty. And then we're also not mentioning important features that we don't need for this presentation. So, or like larger unrelated ScalaCheck stuff. So later I'll try and contrast the real gen to the one we're talking about here, but in the important respects, they're basically working the same in the important ways. There are some differences though. And so the core idea behind a generator is, given some source of entropy, some random number generator, or really a pseudo-random number generator, it's not true entropy, we want to be able to generate A values. That's what a generator of A's kind of means. Like you feed it entropy, or sort of pseudo-entropy, and it gives you back an A value. And so this, you could imagine this gen class being that. It kind of wraps this function that gives us A's out of RNG. But this really isn't enough, because we want it to be deterministic and reproducible. So really, instead of mutating some kind of mutable RNG, what I really want to say is we have some kind of immutable view of an RNG. We produce an A value and an updated view of that RNG. So if the RNG is a sequence, we're going to produce an A, and we're going to step along that sequence and produce the next value in the sequence or something, or move it along forward. So is that clear to people, this kind of mutable versus immutable view of RNGs? The idea is that we can't change the input RNG we're given, so instead we make a copy that has moved forward in the RNG sequence. So that way, if you always pass it the same RNG, you'll always get the same results, and there's like no global variable. There's no hidden RNG inside of the generator that's doing anything. It's all purely functional. Values just sort of flow through it. Hopefully that's clear, because we're really leaning on that property. One thing a few of you might have noticed is that actually this is the state monad. And this is the only time I'm going to mention monads in the entire talk. It's really not essential for any of it. But if you're interested, it's interesting to know that gen is just a specialization of the state monad where the state is always an RNG. I only mention it because it's very concrete. Like there's really not a lot to this, and that's when people rave about the state monad, they really just mean this. There's nothing else to it. And so before we go too far, like why do I care that it's deterministic? Like why should we even worry about it? I claim that it's easier to reason about. That's maybe debatable, but there's I think some real properties that are hard to argue with. So one is that we can ensure that our test code is independent of the test. So for example, if our test framework is using a global RNG, but the code you're testing is also using the global RNG, there's an interaction going on there that's uncontrolled. And you could have problems where you're assuming certain things are true about the global RNG and the test framework is erasing those. So one thing that's nice is this ensures the test framework is getting out of the way of your code. So I think that's a really good one. It also makes it really easy to show your tests are reproducible in the sense that there's no global state. If you feed the test the same RNG, it's always going to produce the same, or RNG value is always going to produce the same results. I think that's good. Another thing that's nice is you get kind of concurrent parallel test evaluation for free in the sense that you don't have to worry about running tests in a certain order. If I have a whole bunch of properties, as long as I feed them deterministic RNG values, I can do it in total parallel, and it won't affect the results, like what order they run. Whereas if you used a single mutable RNG, they'd be sort of contending for it, but also the order they got values back would sort of change the test. And the other thing is that we can break the rules if we need. So if we start in a principled way, we can always break the rules in the REPL if we want to. But if we don't have principles, it's very hard to recover them later. So I sort of claim that this is a better design. I'm curious, though, how many people are persuaded this is a good plan, that we should actually make it deterministic and immutable and pure? So like 4 people. How many people disagree and they're like, this is bullshit. I don't even see why you're doing it. Anyone? No? And so people are waiting to see, which is smart. It's smart that you all are reserving judgment until you see how bad it is. So here's my immutable RNG. And this is not, you wouldn't use this in production, but this is sufficient for demo purposes. It's a 64-bit linear congruent RNG. It's really just a glorified long value, and then a next method that gets you the next value in the sequence. So you start with some random long, you can get the next value in the pseudo-random sequence, and then the next, and the next, and the next, and that's how we get our sort of pseudo-entropy. It's not real entropy, but it's good enough for testing purposes. And in case you're curious, the reason why this works is that it's going to wrap around. If it overflows, if the multiplication and addition overflow, they're going to wrap around into the negative longs. So we're going to sort of be cycling through the 64-bit long values via this. If you were in a language that had unbounded integers like Python, you'd have to do like some modular arithmetic yourself to kind of wrap it manually. But in Java, we don't, so I didn't bother there. I just wanted to call that out in case it was confusing to anyone. And so just to sort of illustrate why this sequence works, Here's sort of a way to generate a random RNG from a global mutable RNG, which is kind of iffy, but for this testing purposes, I think it's okay. And then I can just sort of show you that we can call next on these RNGs over and over again and get different. They certainly look arbitrary to me. I mean, I can't prove that they're random, but right, they seem okay. Right? It's not the same value over and over again, or something like that. So this is the RNG we're going to be using for the entire talk. So when you see RNG, you can think of this class with basically wrapping along with this next function, and then this way of producing a random RNG at the start if we need to. And so just to illustrate it, using this in a slightly fancier way, we can take a random RNG and generate a stream of random bytes at a very low level by generating basically following the RNG stream out to 6 elements. So we have a stream that has 6 things in it via iterate. And then we map those RNGs to a byte representation of the seed. So we truncate off most of the bits, and we're left with 8 bytes. And then that gives us this arbitrary looking list of bytes at the bottom. So this is the sort of stuff we're going to be doing, but maybe in a slightly fancier way. Any questions so far, by the way? I'm going to have to move a little bit fast during this talk, but hopefully, if people do have questions, you won't feel bad about stopping me, because I'm happy to stop and try and explain stuff if I'm going a little too fast for someone. So far, so good? Great. So then let's just write some simple generators. So here are 3 simple generators. Basically, what they're doing is they take an RNG in, which is R, and then they basically do stuff with, they're all based on using a single long. So they use the seed, and they do something. The long generator is the easiest. You just take the seed and return it, and then you move the RNG forward 1 step in the sequence. Bool and character are basically similar, but they have to transform the long value. So in the Boolean case, we say, well, I hear that half the long values are greater than or equal to 0, so if it's greater than or equal to 0, we'll say it's true. Otherwise, we'll say it's false, and that's a way to get a random Boolean from a random long. Similar with characters, we say, well, if the longs are random, I can take the first 16 bits, treat that as a character, and now that's a random character, right? It's pretty straightforward. The key to note is that we always have to return r.next. If we didn't do that, if we returned r, we wouldn't move our RNG forward, and if you reuse that RNG, you'd get the same value over and over again. So we'd be stuck in some kind of terrible world where things never changed. Which usually we want to be in as functional programmers, but in this case we actually don't want to be in. We want things to change in a kind of a controlled way. So we always want to advance our RNG, because we basically used up that seed value. We did something with it, and now we need to move the RNG along so that someone else doesn't also consume that same seed, if that makes sense. And then here's sort of still it's a simple generator, it just uses a single seed, but it's a little fancier. This is, a lot of random number generators use this sort of trick to produce values between 0 and 1. So what we're doing is, we're taking 53 bits of the long value, the sort of lower 53 bits, so it's going to be a long value between 0 and some relatively large number. And then we're multiplying it by this really small double value. And that turns out, if you do the math, it turns out to give us values that are always between 0 inclusive and 1 exclusive. So it's values that are always less than 1 and always greater than or equal to 0. And this generator ends up being really, really useful for a lot of stuff. It's basically similar to like the rand function in C or something like that. But immutable. And so we're doing the same thing, though. We're returning this fancy double value along with the next step in our RNG. But one thing you've probably noticed if you've gotten this far is that there's a lot of boilerplate. We're always calling r.next. And if you forgot to do that, it would be catastrophic. It would be really bad. Your generators kind of would be broken. So it's bad that you have to remember to do it, and you're going to be writing all these generators and doing that everywhere. So we'd like to eliminate that boilerplate, since it looks super mechanical. So what can we do to eliminate that boilerplate? And the answer turns out to be creating a map method. Anyone who's sort of used Scala has probably used map methods before, but basically in this case, if we have a generator for A, and we have a way to go from A to B, we can use that to get a generator of Bs. And we do that in a pretty mechanical way, right? We run our generator of A's, we get an A value and an RNG out, we transform the A value into a B value, and then we just return that along with the modified RNG. And that gives us the gen B. I don't think this code itself is complicated, but it's a pretty powerful idea. All the generators we saw so far can be implemented in terms of map on a single generator that produces long values, which is kind of the sort of primitive generator we're going to base everything off of. And so here's those examples. So Boolean is just mapping along into this Boolean space using the same predicate we did before, greater than or equal to 0. With double, we can kind of compact down the math that I did into this one transformation on a long value. And then we can write these other combinators in terms of double. So we can say, give me values in a certain range, starting at 0 and up to this limit. And we do that by multiplying our double between 0 and 1 by the limit. Since the double can't ever be 1, we know that the result will never be limit, but it'll approach limit very closely. And when we truncate that down to an int, we'll get the next lowest value. So up to is going to give us, it's a little bit like the range operator in Scala, like 0 until limit, basically. And then 1 in, we can then use up to get sort of like a probability of like a 1 in 6, like a die roll type thing. Like I want a 1 in 6 chance, a 1 in 2 chance, which is like a coin flip. 1 in 28 chance if you're going to play Dungeons and Dragons. But we can basically stack these combinators by using map to keep transforming those values, which is pretty interesting. And a thing to note is that 1 in produces Booleans just like the bool one does, but they produce them at different distributions. So they're not actually the same. Bool gives you kind of a 1 in 2 chance. 1 in gives you like a 1 in n chance, potentially much smaller than 1 in 2. So that's an interesting thing to note, is that the type signature does not tell us everything about these things. It tells us the values to be produced, but it doesn't tell us the frequency or the distribution of them. And I think that's important to kind of call out now, and we'll revisit that later. And so you might not take my word for this, so let's maybe test it out, make sure it all works. So I've implemented this D6 generator, like a 6-sided die, and going to generate, if it works, it generates uniform values between 1 and 6. And then I'm going to take 10,000 samples of it. I'm going to run this generator 10,000 times. And then I'm going to build a histogram to look at the frequencies to see if the distribution is plausibly uniform or not. There's actually some really fancy tests you can do with like die hard and die harder, but we're not going to do that here. We're just going to kind of eyeball it. And so if you eyeball the histogram, to me it looks like it's plausibly a normal uniform, not a normal, uniform distribution. If you roll the 6-sided die manually and recorded it 10,000 times, you might get something that looks like this. You're not getting one. It doesn't look like a massively loaded die or something. Cool. So simple generators using like one seed value. Well, what did we learn? Well, it seems like it works, which is cool, and that map and long are enough for basically all simple generators that just consume up to 64 bits of entropy from our RNG. If that's all you need, you can just start with the long generator and then transform that long value into whatever you want, and it all works. One thing that's cool when we do it this way is that our RNG is pretty much implicit. Like we mention it in the long generator, and that's it. You never see the RNG in any of the other generators, which is good because usually if someone's working with an RNG, it's like an opportunity to fuck it up, basically. And so I think it's good to kind of like keep that away when possible. One thing I mentioned earlier is that we kind of want to be explicit in the documentation about the distribution and range because that's not in the type signature. Like you might wish it were, but it's just not. And that from a really small kernel of functionality, we've already been able to build a lot of generators that you might use in your tests, but not all of them. So we've left out type parameters. We've left out generators that need more than 64 bits of entropy. We've left out all the collection types. We're not really showing how to thread RNG state through complicated situations. Like right now, we're only having to thread it through these like very simple generators. And the whole promise of this talk is that we're going to get to functions and exotic types, and we haven't gotten there yet, just to acknowledge. So let's start with a generator that we sort of already mentioned, which is a list of A. That we use that for our take method, our sort of take 10,000 samples. It'd be nice if we'd actually done that with a generator as opposed to the kind of hack we did with sample. So what's our game plan? Well, we're going to use generators recursively. We're going to thread RNG state through very carefully, and then hopefully we profit. Hopefully it works. And so I'm just going to jump you right to it. There's no suspense. This is what I claim is a correct implementation of this. And let's take a little bit on this slide because it's a little bit subtle what's going on. So basically, this is a fixed size list. You give me a concrete size and a generator of some type, and I claim in response that if you do that, I will give you back a list that has that many elements, random elements of that type. So if you give me a generator for doubles and you give me the number 3, I'll give you back a list with exactly 3 doubles in it. That's the claim. And how does that work? Well, if you give me 0, if you want 0 or fewer, it's pretty easy to do that, right? I just return you a constant nil. It's always going to return nil. And that's the easy part. The hard part is if I give you a number that's greater than 0. So in that case, well, what do we have to do? Well, since it's a list, we need to do 2 things. We need to generate a head and a tail. Head is a single A value, and the tail is 0 or more A values. But it's not just 0 or more, it's exactly n minus 1. If we wanted the whole list to be n, and we produce the head, which is 1 element, we want the remainder, the tail, to be n minus 1 elements. So that's where this n minus 1 is coming from. Basically, we generate the head directly using the generator that someone gave us, and then we recursively call our own generator, but with a smaller size. So the size is reducing. So that's how we build the tail. And once we've built the head and the tail, then we cons them to each other, and we've now produced a list of the right size. Assuming that we produce the right tail, consing on one element will produce the right total list of the correct length. And I guess the reason why I said it's tricky, because maybe you don't even think this looks tricky, is notice that we have RNG0 coming in as the initial state. And then when we run our first generator, we get back RNG1, which is an updated RNG based on RNG0 being used. And then when we call the method recursively, fixed list, we pass in RNG1, and we get back RNG2, and then that's the one we return. It's very important we got that right. If we screwed that up, again, like our generator would be messed up, and either we would be wasting space of the RNG sequence, or we'd be reusing RNG state over multiple generators potentially. And that would be very bad, because you'd notice weird patterns in your data you were generating. You'd notice like repeated sequences and stuff that you wouldn't have wanted. And so it's very important to get that right. And that's why I said we have to kind of thread this through carefully, because you see that parameter getting kind of threaded through. Every time we evaluate a generator, we end up doing this threading manually. And it's a little bit ugly. So any questions about this?
This is not tail recursive.
It's definitely not tail recursive. And that's why I said, so for the purpose of this talk, we're not worrying about efficiency or tail recursion. There is a tail recursive way to do this, for sure. It's just, it didn't necessarily illustrate the point I wanted to make on the next slide. And it's just a little more code. But yeah, you could totally do this in a tail recursive way. And that's ultimately how ScalaCheck actually does it. And so then, if we have fixed list, we can now generate a dynamically sized list if we take size itself as a generated parameter. So then, in this case, we actually generate the size we want, and then we evaluate the fixed list for that size. And this now produces us lists of between 0 and whatever the max value that size can produce. And again, if you think about back to our map example, it seems like we have this kind of threading pattern we're doing repeatedly. It's a repeated pattern, and the more of these generators you write by hand, the more you're going to do this threading. And you'll notice it's kind of like boilerplate again. It'd be nice if we could get rid of it. And it turns out, in fact, that we can. So probably some of you saw this coming, is that in addition to map, we can introduce flatMap. And flatMap is the way that you remove this kind of boilerplate. So what is flatMap? Well, what flatMap is it says, instead of going from an A to a B like map does, it says, if you give me an A value, I can give you a generator of Bs, but then that generator has to be fed additional RNG state to produce its B value. It can't just use the A value to do it. It has to actually it needs additional RNG state. And so if you look at how it works, we run our first generator to get an A value and an updated RNG. We then transform that A value into a generator of Bs, and then we feed the generator of Bs the updated RNG state, and it will produce the B value and the actual RNG state we want. So again, pretty simple but very, very powerful piece of code here. And using that, if we go back to our example, and this is why I didn't want it to be tail recursive, you can now, I think it's a good illustration of flatMap. So if you look, all the RNG is gone. We don't mention the RNG at all anymore. We just say, generate an A value, and then using that A value, now generate me the tail with fixed list, and then we're going to do map. We're going to map over that generated tail and prepend the A value back on, cons it as the head. And this is all we have to do to generate lists of a certain size. So we remove any mention of the RNG. As a comment, I also included this with a for comprehension list. I almost think the for comprehension is too magical. Like, I think if you write it this way, it's not even clear to some readers like what's going on. Whereas if you write it with flatMap, it's a little uglier but more explicit. But you can write it this way, and it's very, very elegant looking, in my opinion. The A and then the A's and then consing them together. So these are equivalent, and this is what you can do with flatMap. And so similarly, with our dynamic list, we just flatMap over the size, and then we just call our fixed list combinator. So any combinator that takes some input values and produces a generator can now be easily made dynamically generated using this flatMap approach. And so up to 1in, all these type of combinators suddenly become much more powerful when you have flatMap. And I can illustrate that on the next slide here. So here's some generators for option types, either types, tuples, that all take in generators for some sort of parameterized type, like A or B, and then they produce some more interesting structure. So in the case of option, we have a generator that if you tell me how to make A's, I can make option A's, and I can do so at a particular frequency. So the way that I did it, as I said, I have a 1 in 10 chance of being none, and a 9 in 10 chance of being some A. So that, and we're using flatMap because we need to dispatch to the generator we were given if we want to build a sum value. First, we generate a Boolean, whether or not we want it to be none. And then once we've done that, we then generate either a none value, which is easy, or a sum value, which requires to using the underlying generator. And similarly for either, we have a coin flip. And then once we've generated that coin toss, if it's true, we go to the right, and if it's false, we go to the left. And we only ever use one of those generators depending on that Boolean value. And so that's another case where flatMap makes this really elegant. If you did this with manual state threading, you could still write it, and it'd be OK, but it would be much easier to get wrong, much more fiddly. And then finally, I just included tuple here. Tuple isn't very interesting from my point of view, but it's powerful, and you need to use it. So that's just how you would do it here. It's literally just a flat map and a map to build up a tuple. Questions about any of this? Because things are actually going to accelerate, believe it or not. And so here's some more generators, just to kind of shoot them into your eyeballs. We've got sets, vectors, maps, strings. And basically what we're doing is we're building in what the max length is here. And that's one thing to also call out is that I, the author, am making a choice about how big I want my sets to get. I don't want sets of 1 million elements. If you do, you might need to write your own generator in some cases. And so these generators have a built-in notion of size. ScalaCheck is a little fancier, but it still has sort of a built-in notion of acceptable size that we'll get to. But if you look, once we can build lists, we can build all the other collections very easily just by turning that list into something else. So for vector, just build a list, and then call to vector at the end in a map. For a set, build a list, then map it and call to set at the end. For a map, build a list of tuples, and then map it and call to map at the end, right? It's all very mechanical, which is kind of interesting. So what did we learn about these fancy generators? Well, flatMap is amazingly powerful, right? I mean, everyone already kind of knew that, possibly. But it's still kind of neat to see it actually happen. And we built product types, like tuples and case classes. We built sum types, like either and option. We built collections. So is there anything we can't do with this? I mean, like, it's a legit question. Like, we've done tons of stuff, right? So like, maybe we can just do it all. Maybe we're done. But my claim is that you can't build functions. And I asked this question. You all came to the talk. You read the description. So it's not really a fair question. But like, it seems kind of implausible that you could use these techniques to build functions, right? I mean, like, how would you do it? Like, you could have a built-in list of functions for certain types. Like, if we want an integer, here's some integer functions I wrote down on a napkin, and I'll choose one of them. But like, that's not really what we mean, right? We mean from some arbitrary types. So how would we do this? And so what do you think? I mean, like, I don't know, show of hands, like, before coming to this talk, like, if someone was like, I want you to build me a function generator, do you think you could do it? Like, how many people are like, yeah, I got this? Anyone?
I could build you one, but you wouldn't like it.
OK, so we got a maybe. And then, yeah, so basically, right. So I was in your position about a year ago. Like, I really wanted these things, but I didn't know how they worked. And so I went off and read QuickCheck. I cheated. I didn't actually come up with it myself. I just read how QuickCheck did it. So, which is often the solution in life.
In this case, how is it different from a function that just ignores the input?
Well, so I'm glad you asked, because yeah, this is my very next slide, putting the lazy in FP. So here's one that's technically correct, right? You can build a const function, right? Like, take a generator of b's, ignore the a parameter, and just always return the same b for every possible a. It's technically a function from a to b, right? I mean, like, it satisfies the type signature, but like, it's pretty much not what we want, right? And you can sort of see here that like, we call it on 100 different integer values, and it always returns the same exact constant double. So I claim this isn't actually useful. Like, I mean, you can do it, and actually ScalaCheck until pretty recently did this. So I mean, people didn't notice. Like, I mean, like, people were writing code that generated functions.
People found bugs, like, accidentally.
Right. It didn't test as much as they wanted, but like, you can actually go pretty far with this approach, but it's not great. I'm not satisfied. So let's try it again. And then this is one that maybe no one really believed would work, but let's at least look at it where, OK, we have this messy way of sampling a generator, just like with global state. Let's just do that. Let's just, every time you call this function, we'll generate a random b value. It's a function from a to b, right? You put in a's, you get out b's. Sounds good, right? And they're not constant functions. I mean, they're going to change all the time. And so, right, so the problem with this is that they're not constant functions because they're not functions, right? They're neither constant nor are they a function. You pass in the same value and you get different results out of it. So it doesn't really satisfy our intuitions for how functions work. So I claim that wild function, just like const function, isn't actually good. Maybe it's good for some tests. Maybe you have a certain test where you actually want this behavior, but in most cases people don't. So are we stuck? Well, let's take a step back and think. So in our cases, we're using gen b, and so we need a generator for b's. If we didn't have that, we couldn't do it. But we're not requiring anything for a's, and that seems kind of weird, right? Like, if we need a generator for b's, we probably need something for a. It probably shouldn't be a generator, but it should be something, right? Like, if we don't mention a at all, how can we claim that it's really a function from a values to b values if we're only using stuff about b? So what gives, basically? This is my sort of intuition. And so my way to summarize a generator is it's basically a function that consumes RNG state, so it takes an RNG, and then generates a B. So that's what's going on. It's consuming RNG state, generating a B. We sort of want the opposite of that. There's like this trick in functional programming where whenever you need to do something interesting, like reverse everything, like switch it around, opposite, and that often yields something good. So maybe let's just try doing that because we're sort of stuck. And so what if we consume A's to generate RNG state? Instead of consuming RNG state to generate B, what if we consume A and generate RNG state? We've reversed the sentence. And how do we do that in the types? Well, we consume an A and generate an RNG instead of the reverse, right? So we're going the opposite direction. OK, so let's assume this is a good idea. I haven't proven that it is, but let's just maybe it is. So we'll call it cogen, because you put co on the front of something when you reverse it. And we'll say, well, instead of run, we'll call it rewind. I don't know if that's actually a bad metaphor or not, but it's just the one that I went with. So instead of running it to get a B, we're kind of like rewinding an A value into the state somehow. Maybe like consume or like suck in, or I don't know. Anyway, and so I built one for long. So what's it doing? Well, what it's doing is it's taking a long value in an RNG, and it's sort of incorporating that long back into the RNG state via this XOR operation. It's XORing the bits, and then getting some random RNG out of it. And so in some sense, the RNG that's produced is a result of influenced by both the RNG you passed in and the long value you consumed. And so that's what this cogen is doing. And then it's also calling next just to move the sequence along. If you've worked with RNGs, this is like essentially like a very simple reseed operation that we're reseeding it with some input value we were given. So what can we do with this? Well, can we kind of plug these things together? If we have a cogen of long and a gen of bool, what can we do? And so I wrote this real naive thing, which is just like take in an RNG and a long, run the cogen, get an RNG, and then run the generator. Like that, OK, so we've got this function that takes two things and returns one. Like, cool, it's not what we wanted exactly, but it's like, it's something, right? So maybe, what can we do? Well, if we start with this, we're in functional programming land, we can maybe curry. So what happens if we curry the function? So instead of taking both parameters, it takes just the RNG and then produces a function that takes the long and the Boolean. Well, if you squint, we just built a generator, right? That's what it is. We took an RNG and we produced a function from long to Boolean. That's exactly what we set out to do using this cogen thing. So if you look, we bind this RNG0 into this anonymous function that takes an n, and then it combines the RNG0 and the n into a new RNG, and then we run our B generator that we were given on the result, and we get a B, or in this case, a Boolean. So pretty great. I mean, let's just actually see if this works. So we'll take 5 random inputs. We'll build a random f function, use recombine to do that. We'll build a different function, g, and we'll basically run it through the inputs twice each to make sure that the inputs are the same for f and then different for g. Of course, I could get really unlucky, and it actually happened to randomly generate 2 functions that produce the same values for 1 through 5. In this case, it didn't, though, and I was lucky, and it's good. So you can see that the 2 maps at the top line up. So that means the function was deterministic. And if you look at the bottom, it means the function was distinct. It wasn't producing the same kind of function for 2 different random seeds. So it appears to work. Pretty cool. How many people think this is cool? Maybe I'm like, OK, so like half of the people think this is cool. Great. And so if we kind of, yes, Daniel?
I have a really good question. Maybe I'm jumping ahead, because I don't know if there's actually a solution to this. But so are you actually throwing away sort of a state lineage inside of the function, right? Because you're throwing away the RNG that we saw.
That's a good question. So I'm not going to deal with that in detail. But yeah, Daniel's point is that if you look, actually I'll go forward to the generator. If you look, we're kind of binding RNG0, but then when we run it, we're kind of throwing away the RNG state. And that's true, and that's kind of why you need a reseed operation, because really, in the actual thing, your reseed is not just going to be like an XOR, it's going to be jump to some random other part of the RNG state. And so if you do that, if you reseed in that way, you don't have this problem that like you're going to overlap with other people's RNG usage, because you've jumped to like a pretty unique point in the large RNG cycle that like no one else is likely to be at. And so you're right. That's like is a sort of a theoretical problem, but if you reseed correctly, you don't in practice have that. But so jumping back to our talk here, this is how our actual generator looks. We take a cogen of A, a gen of B. We build a generator, and we do have to mention the RNG. That's one thing to note. We can't use map or flatMap to define this. It's like a little more powerful than those. We have to actually take the RNG and then build an anonymous function that uses that RNG plus a provided value, smash them together, get a new RNG, and then run the generator on that and take the B that we get out. And that's f is our function here. So The talk has managed to hit its primary goal in the allotted time, which is great. And so let's keep going. So we have a cogen long, but how do we make others? We probably want to have functions that not just go from long, but from other types. Well, the answer is this contramap function. And so contramap is like map, but in reverse. Cogen is sort of like the reverse of gen in a whole bunch of ways, including the fact that it doesn't have a map method. It has this funny backwards one called contramap. If you've worked with Scala's ordering, it has a similar thing. Like on and by are sort of related to contramap. They're kind of like map in reverse. So in this case, what it sort of says is if we have a cogen of A, and we have a function that takes us from Z to A, instead of from A to something else, we're going from Z to A. If we can do that, then we have a cogen of Z. And the reason for that is that if we know how to rewind an A type, and we can translate a Z type into an A type, we translate the Z, then we rewind it. And that gives us a cogen for Z. So similar to map, but kind of in a reverse direction. And we can use this to build cogens for types like int, boolean, double, short, anything that has 64 bits or fewer of state, basically. Anything that can be represented uniquely as a long in some encoding can be contramapped into long to build it. And so boolean's an example here. If it's true, we use the long value 1. If it's false, we use long value 0. Those could be any two values. They don't have to be 0 and 1. As long as they're two different values, that works equally well from the point of view of a cogen. And here's a few more. So here's the integer one. Just treat the integer as a long, and we're done. Double's a little weird. We use this like funny way to get the long bits of a double. Pop quiz. How many people know the difference between double to long bits and double to raw long bits? Anyone? No? OK, great. Never mind. I'm just going to ignore that whole line of inquiry. So OK, and then we can do, but here's an interesting one, cogen for list. So if we want to consume an entire list, how do we do that? Right? We know how to consume a single A value. We have a whole list of them. The answer is that we actually fold. We fold over the list, and the accumulator is our RNG state. And so the idea is we start with an initial RNG state, and then for each element in A, we consume that. We combine that with the RNG state to get a new one. And at the end, we've consumed the whole list. The whole list has had a chance to influence that RNG, and the one we get back is guaranteed to be dependent both on the RNG it used, but also on all the values in the list, which is important. When you build a cogen, the important thing is you have to consume the entire structure or let the entire structure influence the result. If you don't do that, you're going to get situations where two values that are distinct will always be treated the same, which is not desirable when you're writing these sorts of tests. So you need to kind of consume all the input. It's a little bit like writing a hashing function. In fact, if Bill Venners were here, he would like yell at me for writing cogen, because in theory you can use a hashing function for all of this. But I think that's a little bit ugly, and I think this approach is a little nicer. So anyway, sometimes when you're doing this kind of stuff, it makes sense to just kind of go nuts and see if it breaks. And so in this case, let's just not do long to Boolean. Let's do like list of int to list of double, like something that like would be easy to screw up and seems pretty complicated. So I've got a cogen for list of int. I've got a gen for doubles, and it's going to be fixed list of 2, so it's going to always have exactly 2 doubles. And I'm going to generate my f, and then I'm going to run it on some lists. And you can see that it's producing arbitrary-looking pairs of doubles based on these different lists that I've passed in. So pretty cool, right? Let's see, how are we doing for time? We have 50 minutes. Actually, I'll jump to the REPL then if we have a little bit of time. So there's this cool thing I wanted to do, but I wasn't sure if I had time for. But it looks like I will, where, let's see, let me do this.
Did you hit enter? Yeah.
Oh, geez. All right, so let's see live coding without the source code. Actually, I have the source code. Why don't I just go to it?
So, Erik.
Yeah?
While you're typing and trying to gather your thoughts, I thought that the ScalaCheck called it perturb rather than rewind.
It does.
Is that a very different function?
It's called perturb in ScalaCheck, but it doesn't. Perturb is, if you're thinking about it from an RNG-centric point of view, perturb makes sense because you're perturbing the RNG. But in this case, it's a generator-focused talk, so I didn't want to perturb. I don't think that people have any intuition of why you would call it that. And so I called it run and rewind as sort of like a linear direction metaphor. But the name is arbitrary. It's the same exact thing. It works the exact same way.
So as a data point, as someone who doesn't know anything about this, when I was trying to understand cogen, the name actually helped a lot. Like perturb makes a lot of sense to me, and I know nothing about RNGs.
Awesome. That's great. That's good to know. And in fact, maybe I should do a talk where I do that. So here's what I wanted to do. So now I have an RNG generator. So this actually is a gen that produces RNGs, right? So I have this. So then I can make a cogen that is going to take a a cogen that takes, oh, I guess really what I wanted was actually, I wanted the reverse. I wanted a CRNG. I wanted a cogen, so C-long, contra map. I wanted a cogen of RNGs. I wanted a thing that could eat RNGs. Well, I guess I really wanted both, actually. OK, so now what I'm going to do, if I can do it correctly, is I want to produce a function that takes in an RNG and produces a pair of, let's call it double and RNG. Oh, this should be CRNG, sorry. OK, so what I've done now is I now have a generator for functions of the shape RNG to double and RNG. But if you look at that, what is that? But that's basically the type signature of gen. So now I can map this into a gen. So my GG is a generator of generators. I've now got a generator that can produce arbitrary generators. If you give me a generator of A's, I can produce a generator that produces arbitrary different generators of A's that will have different behaviors but satisfy the generator. And so if you wondered how you could test ScalaCheck, you can actually do this. You can write generators of generators and then make sure that ScalaCheck's own invariants apply to arbitrary generators once you have function generators. So like one weird thing about why this might be cool is that you can, any of your classes that are isomorphic to functions, you can now generate them in this weird way with arbitrary method implementations. Pretty interesting, right? Awesome. And I should probably just prove that this works. So I have GG, now let me sample it. Let's call it arbgen. And now if we do arbgen.sample, so now we used generator to generate some arbitrary generator, and now we're sampling it and we're getting doubles. I can't prove to you that it is always distinct, but I just wanted to illustrate this because I didn't put it in my slides, and then I laid it to this morning I wished that I had. So let's go back to the talk, back to the real world. And hopefully we still have enough time. 8 minutes. All right. So then going back, we're now in the ScalaCheck world. We're leaving my nice world of nice, clean generators that I just showed you, and we're going to actually show how my actual generators are implemented. So this is how Jawn's JavaScript generators, AST generators are implemented. So I have a bunch of really simple generators using ScalaCheck's combinators for my primitives, like null is a constant. My Boolean type is a one of. It's either this or that. And then I basically use some arbitrary as this type class that gives you like a random distribution, a sort of arbitrary distribution for free. Like you don't have to mention the generator yourself. So I'm using that for long, double, and string. And if you look, I'm then mapping them into my AST types. And I'm doing a sort of semi-questionable thing on double where I'm filtering out infinite values because JSON doesn't actually have infinite values, contrary to the beliefs of certain JSON libraries that will not be named. And then these types are all atoms, so then I'm generating a JAtom generator that's basically just selecting from one of these with some probability. So this gen frequency says, here's a frequency distribution. I want different values from these different generators based on the distribution. So this gives me now roughly the distribution I want. And then I have some more complicated generators that are potentially recursive or that are building collections for my other types, like arrays, objects. And then J value down here is the very lowest one. And this level parameter I'm using this to limit how deep this recursion can go. So I want these trees of JSON values, but I don't want them to be like a million arrays one in another. I mean, maybe that's a good test to have do once, but I don't want to do that 100 times or 1,000 times in Travis or something like that. So I'm limiting the depth to max level down there in J value. Yeah?
So I've sort of done this both ways, and I'm curious as to what you think is actually the best way to do it. Because like, rather than doing max level, why not just lean on the statistical distribution, right? Like if you're making it really uncommon or comparatively uncommon to generate sort of good max level testing, then it's like you will get exactly what you want, right? Like out of your 100 tests, one of them will be deep.
Well, so Daniel makes a good point, which is that in theory, if you just make it unlikely to keep going, it's very unlikely you'll go deep. The issue that I've had with that is that especially when you run these things like 10,000 times in CI or like 100,000 times in CI for like stress testing, it's very hard to come up with a frequency that is both generates things that are deep enough to be interesting, but don't have a non-zero chance of exploding. In other words, I've actually found it very difficult to do. Like I've done the statistics, and like having a 1% chance for Travis to hang is still pretty bad. Like it's not great. So like when you make that chance low enough, the depths you get are not that interesting. So I found this to be a better approach. I think probably in reality like a combination approach where you allow it to actually get pretty deep, and then you have a cutoff where you say, okay, after like 100, depth 100 or something, just like kill it. Or find some depth where like it actually causes Travis to hang, and then put a manual kill switch like just below that depth, but then let it do its thing with potentially very big values. Yeah, something like that. So one place where ScalaCheck's gen is a little bit uglier is that my function was just from an RNG to an A and an RNG. In ScalaCheck, you actually have params. Params are what control the size parameter. I mentioned that distributions are important. So ScalaCheck has like a size parameter that different generators interpret to describe how big they want to get. And they get to interpret size however they want, so it's kind of not a great system, but it's what we have. So you take params and an RNG and you produce this R. And so R has the resulting RNG, like the new one, but it has an option of A. And alarm bells should be going off in your head, if you've been following along, like how can this be option A? I thought generators have to produce values. What's going on? And ScalaCheck generators are allowed to fail. And I don't love this decision, but we sort of have to live with it. And this is the main thing this is used for is for filtering. You can actually filter a generator, and so in some cases it's not going to produce the real value, it'll produce none. Which sounds fine, it sounds like something semi-reasonable, but the big issue is how many people have used ScalaCheck and seen this error? Raise your hands if you've had ScalaCheck give up and fail a test. OK, so 5 people. So anyone who's had this, it's the most frustrating thing because your test didn't actually fail. ScalaCheck just got sick of running it, basically, is what happened. But this is because when you return none in a generator, that generator, then the whole property kind of becomes none. And so ScalaCheck's like, well, I have to give up on this test case and start over. And it only has some number of times it'll do that before it actually gives up on the property, and then your CI fails or something. And so I really hate this. This is my complete nemesis. So I really don't like filtering. And additionally, these partial generators totally break function generators because the function generator really needs an A value. And option A is not good enough. We don't want to generate partial functions from A to B. We want total functions from A to B. So basically, if you use generators that can fail as the B type in your function, it might not fail, but it's suboptimal, basically. So what does ScalaCheck do to get around this? Well, I went through about 6 months ago and removed all the filters I possibly could from ScalaCheck. All of its internal generators no longer filter. None of them do anymore. So you should get this error much less on the 113 series than you did. Additionally, in a lot of places, we'll now kind of spin in place. So if we do hit a none, instead of just immediately returning none, we'll actually retry up to 100 times to try and get an actual value, which is arguably a questionable design decision, but it's really nice in the sense that again, it means that you very rarely see test failures now because it's willing to do a certain amount of internal work, especially for cases like you're filtering out 0, you're filtering out nan, you're filtering out one bad value, empty string. In those cases, this approach is great. If you're filtering out 2/3 of your space, that's not great. If you're filtering out all 90% of your space, that's really bad because then this spin case will still possibly fail. So worst case, we have to fail and return none, or even in this case, we actually even have to throw an exception because do pure apply guarantees that you're getting an actual A value back or a B value back. So my recommendations are basically you shouldn't use filter. I think you should use, it's almost like a sort of argument about constructive mathematics versus classic mathematics. I think it's better to build up your generator from constructive pieces that you know how they work, as opposed to taking some really big one that's overbroad and then carving out sections with filter. I think that the constructive approach is nicer, easier to reason about, and it will never fail. Whereas the other one, the more you carve out, the harder it is to reason about how your generator will work. So to that end, instead of using filtering less than or equal to 0, you could use gen choose, which sort of does the same thing but says start at 1, give me values between 1 and x. Similar, but won't fail. And also another trick you can use is you can map invalid values into valid values. So instead of filtering, say, if I see these values I don't like, turn them into values that I do like. If you know how to do that, you can basically eliminate filter from your code, but still have the invariant that you need. And finally, like I said, if you minimize the percentage of discarded values, filter isn't so bad. If you only filter out one value, probably it's fine. It's really if you filter out a ton of values that you're going to have problems. Yes, Daniel?
Is it worth just deprecating filter?
Filter is deprecated.
Oh.
If you check.
They don't even notice.
Yeah, if you check 1.13, I think there's an error message about it.
Okay, nice.
So what did we see? Generators actually aren't that complicated. You might disagree, but from my point of view, if you can do it in a 1-hour talk, it's actually not that bad. We went into a lot of detail, and there's really not actually as much to it as you might imagine, including function generators, which I think is pretty cool. It kind of blew my mind when I saw how little you had to do to support them. Determinism, I think, is really important. I just really claim that. Super important. Pure functional programming, I think, can make things easier. I've written this in more imperative style, and it can be good, but it's much harder to be sure you're doing everything right with the seeds and this and the other. If you use map and flatMap, it's very easy to be I'm pretty sure I'm getting this right. There's no way I can fuck up the RNG. There's no way I can fuck up these sort of details, this global state, or I don't have to reason about these different things because they're just not there. And really, the conclusion is you could roll your own property-based tests if you had to. I don't think you should, but if you needed to, you could. And if you're in a language that's new that doesn't have this, you could be the author of foocheck or whatever the language you're working in is. Here's some stuff I've claimed but haven't really proved. is that property-based testing is just writing tests but abstracted. The process of writing the test is the mental exercise of coming up with a specific case is generalized. And I claim that the benefit here is you can kind of maximize this coverage to energy ratio. Like how much of my time do I have to spend writing tests versus how much coverage do I get? The reason I like it is because I actually kind of hated testing because it felt like a waste of time. But you can get so much power here that like if I spend a couple hours coming up with some properties or laws, I catch a lot of bugs, and it feels really good to do that. It feels nothing's worse than spending a whole day writing test cases and not catching any bugs. It's like, why did I even bother doing this in some ways? If I didn't actually find anything, because we all know that there's bugs out there. Also, a thing that I tried to harp on repeatedly was paying attention to distribution and range. That's something that types don't tell you. It's actually very important, and your specific test might need a distribution or a range that the default generators don't give you. So it's worth looking into. Avoid filter, obviously, and don't be afraid to build custom generators. They're actually not that hard. Like once you sort of start working with them, they're really not that complicated, and the combinators that we provide are pretty powerful. Stuff I did not cover. I didn't cover shrinking in any form, sorry. There's some cases where we can be exhaustive, and you can actually know that your property is correct, not just that it might be correct. I didn't cover that. There's a whole different class of strategies to use there. We briefly touched on recursive generation depth, but not in enough detail. There's a cool thing about approximate laws that algebra does, where you have laws that are true with like 99% confidence. They're not always true, but they're like probabilistically true. And there's a whole strategy you can use there to have those tests never fail because you build in the statistical model for how likely they are to fail into the test itself. It's a pretty cool thing, and I encourage you to check it out if it's something that you've worked on. I didn't go into type level combinators like ScalaCheck shapeless that are pretty awesome. And I didn't give you the detailed ScalaCheck walkthrough that maybe you deserved. So I apologize for that. Anyway, basically we're done. Special thanks to Ricard Nilsson for creating ScalaCheck, many, many years ago at this point. It's like a really prolific library. It's been really important to, I think, success of Scala at a lot of places, including places I've worked. So, huge thanks to him. And I want to call out that ScalaCheck would not have working function generators without the assistance of Kenji Yoshida, the author of ScalaProps, also an excellent property-based testing library. Kenji's super active on ScalaCheck, super helpful, and has provided a lot of really good insights and some good bug reporting in getting that feature working. Finally, obviously the library couldn't exist at all without the time and energy of its users and contributors. So yeah, thank you to everyone, those of you among you who might be ScalaCheck users and contributors, and those who might be watching later. So that's my talk, and thank you for listening.